Hello students, in this video we will try to understand two very basic microwave oscillators, okay, high power microwave oscillators, and these two microwave oscillators are reflex klystron and cavity magnetron. These are the two microwave oscillator. That means it must be an electronic circuit which produce oscillation of microwave frequency, that means 10 to the power minus 6 hertz. Okay, microwave frequency 10 to the power minus 6 hertz. These are the frequency which are generated by this devices. Basically we can design these microwave oscillators in lab also, uh, but with very less power. So to increase the power, to amplify the signal, we need these special types of oscillators called as reflex klystron and magnetron. Okay, basically when I say a klystron is a specialized linear beam vacuum tube which is used as an amplifier for high radio frequency. That means from UHF, ultra high frequency, up to into the microwave range. Okay, so there are two types of reflex klystron, low power and high power. Low power klystrons are used as oscillator, and it will be used for communication links, while high power klystrons are used for television transmission, satellite communication, radar transmitter, and sometimes in microwave ovens also. So these are the basic applications where we are going to use these devices. So when I say the first one, reflex klystron, it is basically a single cavity klystron in which the electron beam is reflected back from through the cavity resonator by a repelling electrode having a negative voltage. It is used as a microwave oscillator, also known as reflex oscillator. You can see the diagram. Basically what the reflex klystron consists of. It is a vacuum tube. On the one end you have electron gun assembly, and the other end of that has a repeller electrode. Okay, what you can see is the repeller electrode is connected to the negative potential. Okay, that is repeller voltage VR. Similarly, the electron gun assembly also has a connection to the anode voltage, where we have connected it to the negative terminal of the anode voltage. The other two are called as anode cavity. The two cavities which has been shown in the figure is called as anode cavity, out of which one will be used to take that radio frequency output. Okay, electrons, the basic principle when we discuss is when the electron beam will be emitted by the electron gun assembly, it will pass through this cavity, go to the repeller space, and as you can see, the repeller electrode is connected to the negative potential. The electrons will be repelled by the repeller. Okay, and all these electrons will be fed back to the anode cavity, where it will form the bunch and the RF output will be taken. Let us discuss principle of operation of a reflex klystron. Okay, I have given you a basic idea of what exactly a reflex klystron is in the previous slide. Now, a reflex klystron utilizes the phenomena of velocity and current modulation to produce oscillation. We will individually understand what exactly we mean by velocity modulation and current modulation. Okay, velocity modulation, I'll just give you an example what exactly I mean by velocity modulation. Electrons are moving towards the repeller electrode. As the repeller electrode is connected to the negative potential, what it will do is it will repel these electrons, and these electrons which will be repelled by the repeller electrode will move towards the anode cavity with less velocity. Okay, so that is what is called as velocity modulation. And when these electrons are bunched, we will study that also, what exactly we mean by bunching of electrons. When bunching of electrons is formed inside the anode cavity, current modulation takes place. Okay, A reflex klystron consists of a single cavity that performs the action of both buncher and catcher cavity. As we have seen in the diagram, we have anode cavity. Okay, so this reflex klystron is a single anode cavity klystron, okay, which will be used for both bunching as well as catching the electrons. So as to have oscillation, feedback is needed to be applied at the input, which is provided by the oscillator. While moving electrons undergoes velocity modulation and the repeller applies repulsive force on them, this leads to the formation of bunch of electrons. How? We will try to understand in the next slides. Further, this bunching will lead to cause, as I said, the bunching of the electrons will lead to cause current modulation. A reflex klystron utilizes the phenomena of velocity and current modulation to produce oscillation. A reflex klystron consists of a single cavity that performs the action of, as I said, both buncher and catcher cavity. As to have oscillation, feedback is needed to be applied, and of course as the input which is provided by the oscillator. In this slide, you can see the basic structure of a reflex klystron. What you can see is there is a vacuum tube. On one end, there is anode cathode heating element. We also call it as a gun assembly, which will emit electrons, right? And on the other side of that, we have a repeller electrode, okay, which is connected. This is the repeller electrode. This is the repeller electrode, right? This is the repeller electrode, and this is the electron gun assembly, which will emit the electrons. Okay, now what you can see is the electron gun assembly is connected to the negative potential of the anode voltage. Okay, similarly the repeller electrode is connected to the negative potential of a repeller voltage. We call it as this V and VR. This is VR, repeller voltage. So what happens is electrons will be emitted. They are negatively charged. These electrons will move towards the repeller, and as the repeller is also connected to the negative potential, they will return back to the cavity. Okay, and these two are anode cavity, which will be used for bunching as well as catching electrons. And as there is bunching and catching of electrons, as I said, as the electrons is moving back, there will be a velocity modulation, and when these electrons will bunched in the anode cavity, there will be current modulation, and by using one velocity modulation and current modulation, a microwave frequency output will be produced by a reflex klystron. Okay, now when we understand the operation, we understand this operation by considering three types of electrons. We call it as EE, that is early electrons, ER, that is reference electrons, and EL, we call it as late electrons. Okay, so EE, that is early electrons, will have high velocity, so they will penetrate more into the repeller space, and then it will be repelled back to the cavity. Reference electrons are the electrons which are in the normal condition. That means they will go and again repelled by the repeller electrode, and they will move towards the cavity. And late electrons, okay, so more the velocity of the electrons, more will be the velocity modulation of that particular electron. So what happens is these three types of electrons, when they are repelled by the repeller, they will bunch in the anode cavity. And that is what is produced current modulation. That is what is called as current modulation. And when current modulation and velocity modulation is produced, an RF output will be produced. Okay. As we discussed in the previous slide, the structure consists of a cathode and a focusing anode. that combinedly acts as an electron gun for the tube. The cathode emits the electron beam which is focused inside the tube by the focusing anode. Also, a positive potential is provided as input which sets up electric field inside the cavity. As it is a single cavity structure, the single cavity acts as buncher and catcher cavity separately. As the time of forward movement of the electron beam, it acts as a buncher cavity, while at the time of the backward movement, it is a catcher cavity. The repeller plates that causes backward movement of the electron beam is present at the opposite end of the electron gun, which we have seen in the diagram. The potential at the repeller is made extremely negative in order to permit repulsion of like charges. Repulsion is necessary in order to build electric oscillation, as output power must be fed to the input. So the velocity modulated electrons must have to travel a backward path in order to provide feedback. Thus, a repeller is used in the structure of the klystron. Next, working of reflex klystron. Now, initially, when the electron beam is emitted by the electron gun, then the early electrons, as we mentioned it as EE, early electrons experience a very high potential. Due to this, a strong electric field gets generated inside the cavity gap, leading to cause movement of electrons towards the repeller. As I said, the early electrons will penetrate more into the repeller's place. It will enter more into the repeller electrode. Thus, a strong electric field gets generated inside the cavity gap, leading to cause movement of electrons towards the repeller with a very high velocity. Due to high velocity, the electrons penetrate deeper into the region of the repeller and thus require greater time to repel back towards the catcher. Understood? As it is penetrating more into the repeller space, that means more towards the repeller electrode, it will take more time to come back to the anode cavity, and then the reference electron. But when the externally applied potential is almost zero, then the electrons moves with a uniform velocity with which it was emitted by the gun. These electrons are generally known as reference electrons. Okay, so there will be a reference electrons, ER, which is a normal movement of electrons. So as the power is less, it will penetrate less into the repeller space. So they will come back earlier as compared to the early electrons. So in this case, ER will not penetrate deeply into the repeller surface and get repelled by the repeller in a lesser time than the early electrons. Further, the electrons that is emitted by the gun after the reference electron experience a highly negative potential at the cavity, and this electrons is generally known as late electrons, EL. I gave you the reference of three types of electrons: early electrons, reference electrons, and late electrons. All these electrons are moving towards the repeller electrode, and they are repelled by the repeller electrode. And as they are moving towards the anode cavity, they will reach the anode cavity at different interval of time depending upon how much they have penetrated into the repeller space. So what happens is, when they are reflected back from the electrode, repeller electrode, they form a bunch of electrons at the anode cavity. Okay, anode cavity. The penetration level of the late electron into the repeller space is least, thus takes a minimal amount of time to get repelled back. Okay, so I hope you have understood what exactly we mean by this is what is called as exactly velocity modulation and bunching of electrons. Now in this figure, what you can see is on the x-axis, the above diagram, we can say that display distance from cavity gap has been mentioned, LL, LR, LE. What you can see is there are three types of electrons: EE, ER, EL. They are moving towards the repeller electrode. They are repelled at the repeller space and they are moving back to the anode cavity where they are forming a bunch. It is to be noted that due to deep penetration in the repeller region, EE will take more time than ER while returning towards the catcher. This is evident from the figure. This change in the velocity of moving electrons is known as velocity modulation, and due to this velocity modulation, all the electrons get bunched while returning towards the catcher cavity. This is what is called as bunching of electrons. So in this way, bunch of electrons reaches the catcher cavity. This bunch of electrons leads to cause current modulation. So now you have clear understanding of what exactly we mean by velocity modulation and current modulation. And reflex klystron uses both this velocity modulation and current modulation to produce RF output. Okay. Therefore, at the time of returning, the bunched electron transfers the maximum of their energy to the catcher cavity, thereby leading to cause oscillation inside the tube. The next circuit which we'll try to understand is cavity magnetron. Both are microwave oscillators, okay, but with different type of construction. Okay, so that is what we will try to understand. A cavity magnetron is a high power vacuum tube used in early radar systems. Okay, so this was the basic application of magnetron is used in a radar system, and currently it is used in microwave ovens. It generates microwave using the interaction of a stream of electrons with a magnetic field while moving past a series of cavity resonator. What exactly we mean by cavity resonator, we will try to understand. We will see the diagram and we will try to understand in the next slides. So when we talk about a cavity magnetron, the basic things which we have to understand is the magnetron is a vacuum tube which is used to generate microwaves of high power. Its working principle is based on the interaction between electron stream and magnetic field. The magnetron tube works on direct current power. Okay, if you remember, the only potential, the external potential which we gave to reflex klystron was the external DC voltage. Here we are providing the DC voltage as well as there will be an interaction with the magnetic field. Okay. Now please see the diagram which I have specified in the slide. What you can see is there are two permanent magnets and in between there is a cathode, and there are two electrodes which has been taken out, which will provide the electric supply to the cathode. The electrons will the cathode will emit electrons, and this will provide an electric field. This will provide an electric field within the cavity magnetron, and this external magnetic field will have their effect on the electrons, and which will produce bunching of electrons, and therefore there will be a velocity modulation, and therefore there will be a microwave RF output which will be generated. Okay, so let us see the construction. Magnetron tube is constructed of a vacuum tube having two electrodes. Okay, the permanent magnet and both electrodes are placed in such a way so that the magnetic field of permanent magnet and electric field of cathode are perpendicular to each other. The cathode is in the center of the chamber or the cylinder. There are cylindrical cavities around the cathode, and these are open along their length and connect to common cavity space. Of course, this is not shown in the diagram, but in the next slides you can see the diagrams where we can see the anode cavities. Okay, in case of reflex klystron we had only one single cavity. In case of magnetrons we can have from 8 to 20 anode cavities in a single cavity magnetron. The output of the magnetron is drawn from any one of the cavities by a coaxial line or by using a waveguide. A special waveguide is used to transfer this RF output to the device which has to be operated at microwave frequency. Understood? So this is a three-dimensional figure of a cavity magnetoron. Can you see the center portion? The center portion is the cathode, and the cathode is surrounded by anode cavities. As I said, it can be 8 or it can be 20 anode cavities which will be present. And in the previous diagram we saw there are two electrodes which will be taken out of the cathode, and when DC potential is applied, external DC potential is applied, what happens is this cathode will emit electrons, and when this cathode emit electrons, and with respect to the anode cavity, it will form an electric field as shown in this diagram. This is the electric field which will be produced when potential is applied to the cathode element. There will be an electric field. Okay, so we can understand the operation of cavity magnetoron with reference to three cases: when only electric field is applied, when both electric and magnetic field is applied, and when only magnetic field is applied. So that is what we will try to understand in the next slides. Okay. Now, working of cavity magnetoron. Okay. In the design of the cavity magnetoron, the oscillation is created by the physical shape of the anode rather than external circuit or the field. Mechanically, the cavity magnetoron consists of a large solid cylinder of metal with a hole drilled through the center of the circular face. A wire acting as cathode, this is the electrode cathode which has been present. Wire acting as a cathode is run down the center of this hole, and the metal block itself forms the anode. Okay, what you can see is the different cavities. 1, 2, these are all the cavities which has been anode cavities which are there. Okay. A wire acting as the cathode is run down the center of this hole, and the metal block itself forms the anode. Around this hole, known as the interaction space, are a number of similar holes, resonators. We call it as resonators, drilled parallel to the interaction space, connected to the interaction space by a short channel. The resulting blocks look something like a cylinder on a revolver, right? Where it's like a gun. Okay. That is what has been shown. Remembering that in an AC circuit, the electron travels along the surface, not the core of the conductor. The parallel side of the slot acts as a capacitor, while the round holes from an inductor, an LC circuit made up of solid copper with a resonant frequency defined entirely by its dimension. So depending upon the relative strength of the magnetic and electric field, the electrons released from the cavity moves towards the anode and will navigate through the interacting space. Okay, this is when there is no external magnetic field is applied. So when cathode is heated, electrons will be emitted, and of course they will move towards the anode cavity and they will produce electric field. So this is the first case of cavity magnetoron. When we say the magnetic field is 0, that means there will be only electric field. You can see in the diagram that when the electrons are moving, when the cathode element is heated, electrons will be emitted and they will move towards the anode and they will form the electric field. As we said, if the magnetic field strength increases, that means when you apply the external magnetic field, the electrons which were moving from cathode to anode, they were forming a straight line. But as soon as an external magnetic field is applied, what you can see is there is a curve in the path of the electron, right? That is what you can see when they are moving from cathode to anode. Now they are not traveling in a straight path, they have a curved surface. Okay, so if the magnetic field strength increases vaguely, it will apply to a lateral force bending the path of electrons. If the strength of the electron is made adequately high enough so as to avert the electrons from reaching the anode current becomes zero, right? That means if you keep on increasing the magnetic field, what will happen at some point the curve will be so sharp that instead of moving from cathode to anode, the electrons will move back to cathode, which will be called as bunching of electrons, which will produce current modulation within the cavity magnetoron. So the magnetic field required to return electrons back to cathode just gazing the surface of the anode is called the critical magnetic field or cutoff magnetic field specified by BC. If the magnetic field is larger than the critical magnetic field, what will happen? The electrons experience a greater rotational force and may return back to the cathode quite faster. Now, effect of the magnetic field only if only magnetic field is applied. The magnetic field is applied perpendicular to the electric field. Hence, it's called axial magnetic field. Therefore, the magnetorons are called cross field device because radial electric field and axial magnetic field are perpendicular to each other. If the magnetic field strength is more, the electrons emitted will return back to cathode with high velocity, which may destroy the cathode cavity. This effect is called as backheating of cathode. The most important aspect of cavity magnetoron is the combined effect of electric field and the magnetic field. When both fields are existing, in that case the electrons may have dissimilar path depending upon the strength of E and H, that is electric field and magnetic field. If E is greater than H, that means electric field is greater than magnetic field, the electrons reaches at the anode, but the path will be bent because of small magnetic field. And if magnetic field is more than the electric field, the electron return back to the cathode. Okay, so high negative potential at cathode is created with a high voltage DC power. The cathode emits electron. Path depends on strength and direction of magnetic field and electric field. The magnetic field causes the electrons to get attracted towards the positive anode and start to spiral in a circular path. So what you can see is there will be both velocity modulation and velocity modulation as well as current modulation, which will be produced in the circuit of cavity magnetoron, and therefore a high power RF output, microwave frequency RF output will be produced at the output. In this diagram of cavity magnetoron, you have a clear idea of what exactly is happening inside of the cavity magnetoron when both electric field and magnetic field is applied. So when both these are applied, these electrons then they sweep past the opening of the cavities which are open along their length. Then these electrons inside high frequency radio field in the cavity, due to which electrons get bunched into grooves, that means bunching will happen. Then this field goes into output coupling loop, which in turns connected to the waveguide or antenna depending on the output requirement. That means the microwave frequency which will be produced will be transferred to the RF output by using a simple coaxial cable or a waveguide to a device which will be used, which will require the input as a microwave oscillation. Okay, so this is all about reflex klystron and cavity magnetoron. As I said, they both are microwave oscillator. That means it will produce oscillation of microwave frequency, and it will be used largely in radar system, communication system, and most recently they are used in microwave ovens. Okay, so this is all about microwave oscillation. Thank you so much.